Let's go over some examples for the material we just covered over the max performance equations and our cycles that we were looking at. In this example, we're going to have some data given to us. We've got 4 different sets of data. And the data listed are claimed for a power cycle that's operating between hot and cold reservoirs at a temperature of 1500 kelvins and 450 kelvins respectively. For each case, we're going to figure out if the data they give us tells us if the cycle operates reversibly, irreversibly, or is it impossible. So are they making false claims using these numbers? That's what we're going to do. First, let's go ahead and draw a picture. Our hot reservoir, the temperature is 1500 kelvins. Let's put a little box for the system. And then down here will be our cold reservoir. That's going to be at a temperature of 450 kelvins. Now remember, this is a power cycle, so we've got heat transfer from the hot reservoir. So there's our energy coming in from heat. And then we also have the heat that is sent into the cold reservoir. So we've got that energy transfer there. So that's going to be QC right there. That's kind of hard to read. There. This is a power cycle, so we do expect work to be going out. And remember, for a power cycle, we have QH minus QC for the work of the cycle. That's our scenario, so keep that in mind as we work through all of these problems. In part A, we are told that QH is 600, work of the cycle is 300, and QC is 300. We need to figure out if this cycle is operating reversibly, irreversibly, or if this is like not even possible. So first, let's look at our calculation for work of the cycle. Work of the cycle is QH minus QC. And basically we want to double check that what they're giving us is actually the truth. So we're going to have 600 minus the 300. And that one does indeed check out because that's 300 kilojoules. So this matches that. So that's good. Next, let's look at our eta. Let's look at our efficiency here. Remember, the equation was work of the cycle over QH. Plug in our numbers. We already said work was 300. And then QH was 600. Again, notice your units cancel here. 8 is going to be unitless. That gives us 0.5. Now, we need to know if this is operating reversibly or irreversibly. The way you're going to do that is you're going to find the max efficiency, and then we will compare our efficiency to that. Now, the max thermal efficiency is found using that eta max equation, and that states that it's going to be 1 minus it's going to be 1 minus your temperature there. Okay, so we're going to have the temperature of the cold reservoir. I had to look up the equation. 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. So we'll have, let's move that. We'll have 1 minus 450 over 1500. That gives us 0.7. So this is the max efficiency you could have with this power cycle. Now we're at 0.5. Now that means if we're at 0.5, that's less than 0.7, we must be operating irreversibly. So let's just put irreversible right here. Right? So this is an irreversible power cycle. And again, we know that because 0.5 is less than 0.7. If it was reversible, that'd be best case scenario. It would have equaled 0.7. All right, that's how we do that one. Part B, this one, work of the cycle is 280. Our QH is 400. QC is 120. So let's see if this one makes sense. First thing we want to do is verify this 280. So our work is QH minus QC. So we have 400 minus 120 kilojoules. Gives us 280 kilojoules. So that looks good because that matches this. So far it's possible. Now let's look at our eta, our thermal efficiency. The one for this process that we're talking about right here is going to be W over QH. That gives us 280 over 400, which is 0.7. Now we already found the eta max. Okay, so eta max is 0.7 because remember we use the temperatures here. So this is not going to change even though these numbers here changed because our power cycle is operating between these reservoirs. Those reservoirs are not changing. So the temperatures don't change. Now eta max, like we said, was 0.7. Now if we have 0.7 and the max possible value is 0.7, that means we are at the optimal case here. So we have a reversible power cycle. All right. So the max efficiency we can get is 0.7. So that's like 70%. Two more. This one we have a QH of 700, where the cycle is 300, QC is 500. Remember, the temperatures of those reservoirs don't change. Let's double check this work. So we have QH minus QC. That's going to give us 700 minus 500. And that is obviously 200 kilojoules. Now we're getting 200 kilojoules. They are claiming 300. So they don't match up here. So let's say 300 is not equal to 200. So this is just an impossible scenario here. All right, so they're making false claims with that one. Can't have a power cycle and get that for the work. All right, that one was easy. Let's go to D. This one we have a QH of 800, work of the cycle 600, QC is 200. Let's double check the work, make sure they're telling us the right thing. We get 800 minus 200. That is indeed 600, so that's good. Those two match up. Now we can go on to find our efficiency. Our efficiency equation, remember, is work over QH. We're going to have 600 over 800. Now when you divide these two, you're going to get 0.75. Now, what do we think about that? We're saying this is pretty efficient, right? We're saying that this efficiency with these numbers is greater than the max possible efficiency for this whole system right here, operating between these two reservoirs. Now, is it possible to operate beyond the max possible efficiency? No. So that means this is impossible. You can't be higher than your max value. Our max value is 0.7. We found it right here. We can't exceed that because this is the best possible efficiency we can have with the temperatures of those two reservoirs. So even though they're claiming we got QH and QC and we're getting 0.75, that's not possible. All right, so the answer for this one is impossible. Let's stop this video here. We'll pick up the next example in the next video. See you then.